Alright, so the purpose of this video is to give a preview lecture for lesson 1. What you want to do with every lesson, this is Organic 2, or Chem 2. What you want to do with every lesson is you want to look for the main point and understand the main point first, and then go beyond that and fit the details of the lesson into the main points that you identify. The main points are generally written out for you in the lesson. So you have a printed lesson 1, which is on your D2L website, lesson 1. I don't think you can see it. If I put this here, it's too bright, isn't it? But that's kind of what it looks like right there. I think that's too bright to see. But it has lesson objectives, usually in the bottom panel. And objective number 1 is to understand electron delocalization or resonance. Or I'm sorry, understand how electron delocalization or resonance helps explain the unique characteristics of benzene structure and bonding. So we go to section 1, 8.1 in the textbook, because we're given that lesson 1 is dedicated to sections 8.1 to 8.6. And section 1 is titled Delocalization, or Delocalized Electrons Explains Benzene Structure. That's really mapped over almost exactly to objective number 1. So I'm going to put objective number 1, and I'm not going to write it out because it just gets too busy. But we're led through a litany of phenomena that were understood about benzene, and how if we looked at this structure, and that structure, they all have the C6H6 molecular formula, and these two share some characteristics, which I think is the point of problem number 2 in the text. These two share one characteristic in particular. These two share some characteristics, right? There's a 6-membered ring in both of these. There's not a 6-membered ring in both of these. So so you're led through this litany of characteristics of benzene, and it's real easy to get bogged down in that material there. But the most important point here is that all carbons are the same, and all bonds are the same. Okay, and if that's true, which one of these 3 structures fits these 2 phenomena the best? And the answer is really none of them. Oh, I'm sorry. Yeah, none of them, right? Because that bond is different than that bond, right? And if you draw this, from a sort of introductory perspective, that looks like a single bond, and that looks like a double bond, right? So here's the most important thing, that we are introduced to a new concept, which you've heard before. Actually, it's not new. You got it both at the beginning of this textbook and in Principles or Gen Chem, and that is the idea of resonance. Okay? So it turns out, and that arrow means resonance. That's the important thing here. That arrow does not mean equilibrium. That is resonance. That means these 2 are the same thing. So here's the classic question. I'm going to ask this on day 1, and I'm going to ask it probably many days thereafter. Bond 1 and bond 2. What's the difference between bond 1 and bond 2? That's one way I'm going to ask it. And I'm going to leave this. What is difference between bond 1 and 2? That's the question I'm going to ask you. What's the difference between bond 1 and bond 2? Another way to ask the same question is, what is the bond order of bond number 1? Okay? Here, Will. Right here. All right. So that's the main point of objective number 1. the main point of objective number 2 is draw resonance contributors and resonance hybrids of organic species. That's objective number 2. Draw resonance contributors and resonance hybrids, okay? So let's do an example. I think my favorite example, and probably the one that shows up in every Gen Chem textbook, is, what, can you name that structure there? Pause for a second and name that structure. Soon, that really ought to be an easy one for you, but soon let that be an easy one for you, okay? So what we have to do when we draw our resonance contributors, you learn this in your principles text. You may want to go back and review resonance in your principles text or your Gen Chem text. What we have to do is we've got to make sure with resonance only electrons move. Okay, only electrons move in resonance structures. Okay, you may want to think of a good multiple choice question for a quiz or exam where I would test on that. Only electrons move. What is something that looks like resonance but more than electrons are moving? Okay, so the way that we draw resonance here is boom, and these have to go up there. Okay, now let me point out in my resonance structures here, by the way, I draw brackets around a lot of my stuff here for no good reason. It sort of helps me set things off. And maybe I probably more often do it around resonance structures because it helps me sort of appreciate that these two are the same thing. There are not two structures here. They're the same thing. All right, so objective number 1, I'm sorry, objective 2, I lost my... Objective 2 is draw resonance contributors, which I've done, and then draw resonance hybrids, okay? So what we mean by this then is that this bond here is really sometimes, I almost say sometimes a double bond, and that's not really the best way to say it. We would say that the bond order of that bond is 1.5, and the bond order of that bond is what? It's 1.5, right? Because these two bonds are identical. Stop and think about that. You're not going to like it. That's the main point here of really of this whole lesson, is that these two bonds are identical. Okay? And so these two above are the same thing as this. Okay? Well, that's got a partial minus, and that's got a partial minus on it. Okay? So these two are this, both of them. So let me emphasize that when we draw resonance structures out so that we can appreciate where the electrons are, it's a little difficult to see where everything is here and how many electrons are there. We've got to count the electrons. But these two right here are essentially that thing right there. Okay, that's objective number 2. Okay, and then objective number 3 is to predict the relative objective number 3 for lesson 1 is to predict the relative stability of resonance contributors. Okay, so the example that's given on page 339, the example that's given there is acetic acid. Okay, and if you've got your book open, you can see how resonance is drawn there. But let me draw it out for you. One of the important things to remember with resonance structures is that, first of all, only electrons are moving, and secondly, as much as possible, all atoms have got to retain their octet. Okay, so let's show how we can move electrons here, boom, and boom, and we'll see that all the atoms have retained their octet. Only electrons have moved. And what have I drawn there? If you don't have the book open, take a second. You might want to pause the video and take a second and draw what I've got out here. Okay, that's the product of what I've shown here. All right, now these two are the same thing, right? They're the same thing. Now it turns out though that this does not have, but the resonance contributor is not half and half between these two, because one of these is lower in energy. Which one is lower in energy? The one that's lower in energy is the one that does not have formal charge or does not have a separation of charge. Okay, so to draw this resonance structure, all right, now the point that's made on page 339 is that while these two both contribute to the resonance hybrid, they don't contribute equally. Why? Because this one's far more stable. So the resonance hybrid far more represents this, or far more looks like this, than it does like that. In other words, this is not, the bond order of this bond is not 1.5. It's much closer to what? The bond order of this bond is much closer to what? It's much closer to 2, because this is the more stable resonance contributor. Okay, as a matter of fact, it turns out that this is so much more stable than this, that this is negligible. And when we draw acetic acid, we almost always just draw it like that, and we give no thought to the resonance contributor. Okay, but let me give you an example of one that has a separation of charge, but the resonance contributor is not negligible. Okay, does anybody recognize this? Does anybody recognize this structure? You may not have had biochemistry yet, but this structure is, in general, if I kind of cordon off that and say I'm not going to say what this, leave those as very general things. This looks like a peptide bond. This is the bond that joins two amino acids. Okay, well, we know from the study of proteins that this bond has some resistance to rotation. Has some resistance to rotation. That sounds like a nitpicky detail, but it turns out to be a really big deal in biochemistry, because we know that proteins' structure leads to their function, and the big deal with proteins is their function, right? And so the fact that these things help protein backbones maintain some particular structure so that it can maintain a particular function is a big deal. I'm not going to make a big deal out of it here in this class, but I'm only going to show how here's a resonance contributor that that does have a non-negligible effect, even though one is far more stable than the other. So let me ask you, this will be my final question for this video, let me ask you to draw the resonance contributor over here. Draw the movement of electrons, show it with electron pushing arrows, and be ready for that question on day 1.